Hello, everyone, and welcome to this quick Quake briefing hosted by EERI's Northern California chapter. My name is Elizabeth Angel. I'm EERI's new Communications and Program Coordinator. And we're very glad today to be bringing together Turkish and Greek experts to speak about last October's Aegean Sea earthquake and its impact. Before I hand over today's moderators, I want to say a few brief words about EERI. For those who may not be familiar with us, the Earthquake Engineering Research Institute is the leading nonprofit membership organization dedicated to connecting those dedicated to reducing earthquake risk. EERI has been bringing people and disciplines together since 1948. By joining us, you become a member of our global network of multidisciplinary professionals who are working to reduce earthquake risk. Now I'll turn it over to Volkan Sevilgen, president of the Northern California chapter, to introduce them. Volkan, go ahead.
Hi, everyone. My name is Volkan Sevilgen. I'm the president of the Northern California chapter of EERI. Our chapter is dedicated for reducing earthquake risk, mostly for greater Silicon Valley or San Francisco Bay Area and beyond. This year, we started quick Quake briefings program to learn from our international colleagues and help each other to tackle earthquake risk worldwide. We have a very diverse group of members, and we welcome anyone who would like to join our team to go to our website, EERINC.org. I will just hand over to the microphone, virtual microphone, to Bruce Mason to introduce our great speakers today. Bruce.
Thank you, Volkan. Welcome to the Samos-Izmir M7 earthquake briefing. My name is Bruce Mason, and I'll be one of the moderators today. But first, I want to mention our next briefing that's scheduled for September. It will deal with the magnitude 8.2 earthquake that occurred offshore Alaska about 1 month ago on July 28th. We will feature two speakers. The first will be the Alaska State seismologist, and the second one will be the science officer from the National Oceanic and Atmospheric Administration, the NOAA, National Tsunami Warning Center in Alaska. This will be another great presentation that you won't want to miss. Look for our announcement that will go out early next month. Now back to today's briefing. On October 30th last year, a magnitude 7 earthquake struck the Aegean Sea between Turkey and Samos Island, Greece. It caused much damage, with the worst effects occurring in Western Turkey. We have a full program today with 5 speakers, and they're joining us from Turkey and Greece. Here's the format of our program today. Each speaker will talk for about 13 minutes, and we'll have a question and answer period at the end. The total program will be about 90 minutes today. We welcome question and answers, and how you will do that is you will press the Q&A button you see at the bottom of your screen, and you can type a question. Then behind the scenes, Volkan will go through these questions, and later in our program, he will come back and ask the speakers your various questions. Now, we realize with the full program we have today, we probably won't have time to answer all of your questions. So the speakers have kindly placed their email addresses in their presentations, so you can contact them directly, and in the coming days, they will try to answer your questions. Now, I would like to introduce our first speaker, Dr. Basil Magaris is a seismologist with the EPO-ITSEC Institute of Engineering, Seismology, and Earthquake Engineering in Greece. He will present on the seismological aspects. Dr. Margalis, please proceed.
Thank you very much. I'll try to share my screen. So my presentation is related with seismological engineering aspects of the last earthquake the last earthquake in Samos Island and the cross-border area with Turkey, magnitude 7. And at this point, I would like to thank Dr. Emel Sheikhan and Bruce Mason for your kind invitation in this very interesting meeting. And also my excellent Greek teams that they have contributed in this work from Greece. All these researchers and professors from universities and researching institutes in Greece and also in Turkey, also from the same fields. In this point, it would be a great omission not mentioning a coordinated project by 4 international associations and research organizations: ETAM, Hellenic Association of Earthquake Engineering, Earthquake Engineering Association of Turkey, Earthquake Engineering Research Institute US, and the Geotechnical Extreme Events Reconnaissance Association, producing and publishing a gear report with number 069. Finally, my thanks also extended to my co-coordinators, Professor Sinan Akar for Istanbul, Bogazici University, Istanbul, and Professors Ayşegül Askan and Cüneyt Gülerce from Technical University of Ankara, and some colleagues of my institute, Dr. Nikos Theodoulidis and Ioannis Kalogeras and Nikos Melis from National Observatory of Athens, from Athens. On October 13th, 2020, Samos Meshok was recorded by numerous recording stations located at the epicenter distance up to 600 kilometers. The broader area around the epicenter is characterized by the continental part of Asia Minor to the east and the Aegean Sea to the west. The main topics of this presentation is related to the historical seismic and microseismic effect, seismotectonical information of the area, spatial and slip distribution of the seismic motion, near field strong ground motion recordings. I will try to explain what I mean with near field. Evaluation of the ground motion predictive models, taking into account the records from the Samos Island earthquake. Concerning the historical seismicity, some very strong earthquakes have been occurred during the historical era and the 18th century of this area. The strong 18th century activity seems to culminate with the generation of this earthquake in 1905, magnitude 6.8 and microseismic intensity, epicentral microseismic intensity around 8, causing a lot of damage along the line of the fault, killing 4 people. And of course, it was further up to Suez Canal and the North and the Red Sea in the North Africa. Also, the last significant event in Samos was a last significant event in Samos was the large 1955 6.9 magnitude event. This event was considered to have occurred in the southern part of Samos, in this area, south of Samos and close to Agathonisi Island. The previous information suggests that a similar large earthquake around 7 has not occurred along the Kavstrios fault, that is the fault of our interest, during the last 30 years. So while some strong events may be associated with the eastern part of this area, in the eastern part of the Kavstrios segment, it appears that no known large event of similar magnitude can be associated with the fault, and we can say that suggesting of the recent 2020 magnitude 7 event occurred in a fault that was rather mature. So in all these strong events, despite their large magnitude and extended damage throughout the island, the number of the casualties on Samos was rather small. Actually, in Samos, we have during the last earthquake only two killing people for this strong event, while the 1905 offshore fault event not only have a complex pre-shock and foreshock seismic activity, but also large aftershocks with magnitude ranging around 6. Moreover, both offshore faults events are associated with a similar tsunami phenomena with a significant but localized impact on the Samos Island. Now, concerning the seismotectonic of the area, the adjacent regions, after Kiraji et al. In 2020 EERI report, we can focus in the main seismic zones, seismic fault zones, North Anatolian Fault in Turkey, extended to the Aegean Sea, East Anatolian Fault, and the Hellenic Arc, which is a zone with intermediate depth earthquakes, and some fault segments in the western part of Turkey, close to the area of interest. In the next three figures, you can see some databases, some different databases based on different data proposed by Caputo et al. And Sakelario and Chaburaki from Marine Research Hellenic Center and National Observatory of Athens, Ganas et al. They proposed the same basic fault lines, the Kavstrios fault, the Pythagorean fault, and the Fourni fault, which can affect the area by destructive earthquakes, and also two more Turkish faults. Sorry for my pronunciation with these names. Yavancu fault, I think this one. And please, if the Turkish colleagues have another opinion, please correct me. And Priyan-Salci faults in this area. So all this zone is a zone very active for this place, and can affect the Samos and the adjacent area. Now, concerning the seismotectonic and fault plate solutions, we can see two different type of fault plate solutions with the blue color, the strike slip ones, with the red colors, the normal ones, and with the light red color on Castrios fault is our recent strong earthquake in Samos Island. Historical seismicity and the present century seismicity, you can see, is very intensive for this area. And finally, I'll show you the epicenter, the mesosysmal area of a last earthquake is 1751, 6.8 magnitude, affected this area in the ellipses, and some fault plate solutions associated with the faults, three different faults, Kavstrios, Pythagorean, and Fourni, and the two Turkish faults in the Turkish area. Now, concerning the strong motion networks in Greece, with in a national level, we run two different networks, one from National Observatory of Athens and the other from Czech. And in this figure, in the right figure, you can see all the total 90 records recorded by this earthquake. And the two circles, one with radius 100 kilometers and the other with 200 kilometers, we can see that we have in 100 kilometers only two stations located in Samos Island from Greek point of view, and 9 more ground motion, strong ground motion sensors in distances between 100 and 200 kilometers. Based on this data, and comparing in some cases for the completeness, using the data from AFAD, from the Turkish colleagues, the available strong motion recordings, I'll try to give you some idea about the strong motion recordings in the area just after the earthquake. I hope our colleagues from Turkey will present you also the data from the Turkish network, AFAD, and so on. So in this transparent, you can see all the installations let's say in near field installations close to the fault, and unfortunately, due to the sea, the near fault installations was very few. We have installations from in Samos to strong motion recordings up to 15, 17 kilometers far away, and Kuşadası in Turkey is around 40 kilometers. And as you can understand, the strong motion data in the near field are very, very few. In this photo, you can see the capital city of the Samos Island, Bathi, with the two stations close each other, and the two orientations of the horizontal components of these strong motion accelerographs. In the next two transparencies, I'll give you an examples of acceleration time histories, Fourier amplitude spectra and 5-damped response spectra for three components. For the recordings from NOAA, National Observatory of Athens, and from ITSAC, installed close to one each other. And also in this pertinent subplot, acceleration response spectral values are compared with design spectra from the present building codes currently used in Greece, EAC 2000 and Eurocode 8. And so you can see we have some ideas about the demands in the area. I think the engineers could be more suitable to describe all these effects. So going a little bit further, for microseismic intensity distribution, our colleague Askan and her colleagues gave us a distribution of microseismic intensity based on the empirical relationships between acceleration and velocity in terms of microseismic intensity. So we proposed this map that is in a very good agreement with microseismic maps from previous events. In the next slides, we can see the shake map scenario based on the final fault model for this area proposed by ITSAC just after the main shock, and also this shake map was updated based on more updated seismological data. Taking into account some statistical analysis, number of recordings versus VS30's values and distance metrics JB, we can see that the most stations are classified inside class C and B according to the EERI 98 seismic code, and majority of the data were recording at distances greater than 50 kilometers, so a very, very few near field stations we had. Concerning the distance attenuation of ground motion predictive models, we used a latest model proposed by Boer et al. In 2021 in BSSA. With the dashed lines include bias attributed to systematic overestimation of ground motion in Greece due to, let's say, either regional feature or soil structure interaction effects. Solid curves do not have this. And the second model is based on a worldwide NGA West 2 model from Boer et al. In 2014. And for historical and comparison reasons, also I have included a model from Greece, a very old model, around 2003, from Skarlatoudis and his colleagues. And you can see also the comparison with the data from Samos. using two different VS30 values from two different categories. Now, the same you can observe in the based on spectral values for two different periods, 0.2 and 1. Taking into account only two ground motion predictive model from Boer et al. 21 and BSSA 14. And finally, taking into account the residual analysis, we extract residuals recorded rod D50 intensity measures minus ground motion predictive median estimates with specific VS30 values. And we can see that the consideration of bias factor that we took into account in our model in BE21 improves matching with recording data at near fault stations. On the other side, there is an underestimation of ground motion at stations in distances 30 up to 80 kilometers. So this is you can see this in all figures. Finally, just before closing this short presentation, I'll give you all the available website addresses that you can download the data from the Greek point of view, from EDA, European Integrated Data Archive, from ICHAC, our institute, and also for National Observatory of Athens, that you can download the data very easily. For the conclusion, a lack of strong motion data in the near field distances and high densification of the strong motion network is a necessary duty for our next targets. Distance attenuation of BSSA 14 low Q regions and Boer et al. 21 models is consistent, taking into account the data from Samos Island earthquake. Residuals between the recording ground motions and the median estimates of the ground motion predictive models are fair for the most of the stations that we have examined. And of course, modeling of regional Q in a future ground motion predictive models must be an important duty for us in order to control the ground motion attenuation towards to the long source to site distances. In this point, I would like to thank you for your attention. I hope to keep the time properly. And finally, I give you some basic references that you can find in my presentation in the website. Thank you very much.
Thank you very much, Dr. Magaris. You've covered a lot of material, and I'm glad that we are recording these sessions because I will need to look through the recording to study many of the details. I would like now to move on to our second presentation today. I would like to introduce Dr. Özkan Kale. He is a professor in the Department of Civil Engineering of TED University in Turkey. He will also present on strong ground motion aspects. Please proceed, Dr. Kale.
Thank you for your introduction. I will share my screen. Okay, so today I will present the actually impact of rupture plane uncertainty on earthquake hazard by considering the Samos earthquake extreme motion data. And actually, this is a published paper, and I will present you this study, a part of this study because of the time limitation, on behalf of our group members, Professor Sinan Akkar, Dr. Merve Çağlar, and Professors Ufuk Yazgan and Abdullah Sandıkkaya, all of them from Turkey. And so our main parameter is the source to site distance, so which is the main parameter to define the path effects on the estimated ground motion intensity measures. And in order to calculate the source to site distance, actually, we need to determine the fault geometry, especially for the extended source distances like Joyner-Boer or rupture distance. And in order to determine the fault geometry, we need the centroid moment tensor or finite fault plane solutions, and the differences within and between different solution methods or limitations in data affect these solutions. And so when we consider all the items, all of them affect each other. And at the end, the hazard and risk assessment may considerably affected actually. And we try to determine the level of this effect. And we consider the Samos earthquake data in order to find an answer to this question. So using the Samos earthquake data, we run several analyses in order to understand the extent of rupture plane uncertainty in ground motion predictions and its trade-off within the GMPM modeling complexity for hazard and risk assessment and for more insight about the predictive model development processes. So if I summarize you the methodology that we follow during this study, so at the first step, we collect available fault plane solutions. It can be CMT solutions or can be finite fault solutions. Actually, we consider both of them in the study, but I will only present you the part related to the CMT solutions. And we consider the USGS Global CMT, AFAD, which is the governmental unit in Turkey, and Kandilli Observatory and Earthquake Research Institute CMT solutions. We focused on these four data. And then we collect strong motion data with reliable flat file information, actually. The main parameter is the VS30 for us, and the distance also important. And we gather those data from AFAD and Query, and we choose some representative predictive models in order to make a comparison between the observed data and the predicted ones, and we selected Kali et al. 15 local model, Akkar et al. 14 regional model, pan-European model, and NGA West 2 models, the global models of BSSA 14 and CY 14. And then we generate fault planes from the selected fault plane solutions, and we obtain some ground motion predictions. I will only show you the results related to PGV, and we made some observations considering all the steps. So these are the parameters that we consider in our analysis from the CMT solutions. Actually, we consider the epicentral coordinates, depth values, moment magnitude, strike dip, and rake angles. And among these data, only dip angles differ considerably among them. The rest of the information is similar between the agencies. And we collect the strong motion data, the 83 data from AFAD stations and 10 ground motion data from Query stations. So the most important step in our analysis is the generation of the rupture planes. You can see here the cross-section and cross-section view and top view of a rupture plane. The gray part here is the maximum possible rupture width, and the red one is the generated rupture plane. And this point shows the epicenter, and this is the centroid depth. And we should determine a seismogenic depth considering the tectonic settings of the region. Actually, for our case, we make a quick literature survey to determine a seismogenic depth of the Aegean region, and we fix this value. And then, considering the CMT solutions, we also fix the epicentral coordinate, centroid depth, dip, strike angle, and moment magnitude or seismic moment of the earthquake. And then, in order to introduce the uncertainties, we determine the ranges of the depth top of rupture values, which can be seen here, by considering the studies Maya et al. And Choi and Young's. Then we considering the CMT solutions, and we determine the minimum and maximum values of the rupture areas and rupture lengths. We focus on the Leonard 2010 study in order to determine those ranges. And then corresponding to the determined area, the rupture area and rupture length values, we determine some ranges. Considering the limitations of the seismogenic depth, we determine the rupture width values, the ranges of the rupture widths. And then we determine the corresponding rupture widths and then float these rupture widths randomly along the limitations in these parameters. So we generate 500 rupture plane scenarios from each considered CMT solutions. And so we can see here the solid rectangles shows the surface projection envelopes of 500 rupture planes populated from each CMT solution. So when we compare these boundaries, the surface projection boundaries, actually we can see considerable differences between the CMT solutions and the boundaries, because we create our rupture planes, the 500 rupture planes within these boundaries, considering the AFAT, GCMT, query, and USGS solutions. And thus, the computed source-to-site distances will display variations depending on the differences in these rupture planes. So I would like to emphasize, actually, I listed those GMPMs, but I would like to emphasize one of the features of these GMPMs. Actually, this is the ASP14. This is the regional one. With respect to the functional form of these GMPMs, this is the least complicated one, whereas the Choi-Young's 14 is the most complicated GMPE in this list. So, considering all the items up to this point, I will show you two simple case studies in order to emphasize the assessment of rupture plane uncertainty using recorded ground motion intensity measures. Actually, I selected this one as only the PGV. So in the first case study, we consider all CMT solutions and all rupture plane scenarios. So 500 per CMT solution, and in total 2,000 simulations, the rupture plane simulations we have. And using the measured PGV values and also the predictions of the ground motion models, we calculated the normalized residual values. I called this one as the epsilon PGV, so which can be calculated from the ln PGV observed minus ln PGV predicted over the total standard deviation of the related predicted model. And then we make comparisons of epsilon distributions at two strong motion stations. And we selected Kuşadası and Bayraklı stations. The importance of those ones, Kuşadası is a near station with respect to the rupture planes, and Bayraklı is slightly distant station. And we consider two specific GMPMs for these cases, the ASP14 and CY14. So we can see here 4 panels. The left-hand side panel shows the epsilon PGV distributions for Kuşadası station, and right-hand side shows the Bayraklı station data. And horizontal axis shows the rupture distance, the calculated rupture distance, and vertical one is the epsilon PGV values. And there are 2,000 points on each figure here. So coming from the rupture plane, the simulated rupture planes. So I would like to emphasize two cases here. The one is distance variability and other one is the ground motion variability. And I will show you those cases with the histogram plots. So these plots show the distance variability. Actually, when we consider the distance variability for Kuşadası Station and Bayraklı Station, actually the distance variability is considerable. So for the Kuşadası Station, it's approximately between 15 to 45 kilometers. And for Bayraklı Station, it's 58 to 72 kilometers, depending on the simulated rupture planes. And this is considerable, actually. And when we consider the ground motion variability, so if we evaluate the epsilon distributions shown here, so these are for the ASP14 and these are for the CY14 models. So the ASP14 epsilon distribution display a very narrow band with respect to the CY14. And the reason of this observation, we interpret this one like the simpler functional form of the ASP14 with respect to the complex functional form of CY14 actually. And the other observation is again related to the ground motion variability, but for the between the comparisons about the comparisons between the strong motion stations. So the epsilon distribution is narrower for both models at the Bayraklı site for this site when we compare these distributions with these ones. So the reason of this one, Bayraklı is the distant site with respect to the Kuşadası because Kuşadası is the near station with respect to the earthquake location. And so this can be an indication of lesser impact of rupture plane uncertainty on ground motion estimation at remotely located sites. So in the second case study, now we used all the strong motion stations. We keep the rupture planes constant, but we increase the number of strong motion stations. So before listing the observations, I would like to explain the format of these plots. Actually, we consider all the predictive models that we selected in the study, the ASP14, Kale et al., BSSA, and Choi and Young's. So we considered all the strong motion stations, and these groups shows the strong motion stations, and at each group we have 2,000 simulations at 2,000 epsilon PGV values at these locations. And if I focus on one of the group, so this stripe includes 2,000 rupture plane simulations and 2,000 epsilon PGV values. In fact, all the rupture plane simulations data have different distances, but in order to simplify the figures, we plot the epsilon PGV values considering the mean distance value of this station, the mean value of the rupture planes, actually, the distances coming from the rupture planes. So the epsilon distribution at each stripe is proportional to the complexity of the predictive model functional form, actually. So firstly, if we compare ASP14 and Choi and Young's 14, actually, ASP14 shows the narrowest distribution, but the Choi and Young's 14 shows the widest epsilon distribution almost at each stations. So when we look at the other models, the KH15 and BSSA14, the epsilon distributions of these models range in between the other two predictive models, the ASP14 and Choi and Young's 14, proportional to their functional form complexity. And using the same figures, in this case, we calculated the mean residuals considering some distance ranges, and then we fit some trend lines, the bilinear trend lines, to these mean epsilon residuals. And the overall PGV epsilon distributions from all of the strong motion sites show some interesting results. So if we consider the mean residuals with respect to the mean corresponding distances, so all GMPMs tend to overestimate the measured PGV regardless of distance variations due to rupture plane uncertainty. And if you look at the BSSA 14 model, so this model does not suffer from the inelastic attenuation, because when we consider the distance trends of these models, there's no trend in the BSSA 14 model. This is another interesting observation for this model. And CY14 seems to have the largest bias at short and long distances with respect to the other models. And the regional ASP14 and local KH15 predictor models depict similar epsilon trends. And if I summarize the conclusions, actually our observations depict the importance of rupture plane uncertainty for a few tens of kilometers within the prox of rupture scenarios. And we can say that the predictive models are sensitive to the rupture plane uncertainty with respect to their complexity in their functional forms. And adjustments to candidate predictive models can be used by considering rupture plane uncertainty in order to improve especially for the scenario-based hazard and risk assessments. And lastly, I can say the predictive model developers should consider the distance uncertainty in their models due to variations imposed by the rupture plane uncertainty. And this is the last one. Thank you. And this is the reference of the complete paper of this study.
Okay, thank you, Dr. Kale. We're running a little bit long now, so I'm going to move straight to our next presenter. I would like to introduce Dr. Kamal Oder Siten. He is a professor of civil engineering at the Middle East Technical University. He will present on damage to buildings in Turkey. Please proceed.
Dr. Mason, thank you so much. Let me share my presentation first before I start my presentation here. I am assuming that you can all see it. Bruce, that was an okay pronunciation. I have heard worse pronunciation of my name. I've spent about 4 years at Northern California, more specifically at Berkeley. I know I have 3 names, none of them work. Kemal is like camel, under is like underwear, Satan is like Satan. So that was good, but I would prefer Chetin with the last name. So thank you so much for the introduction. Dr. Sevilgen, thank you so much for organizing this basically briefing and give us the opportunity to share our reconnaissance findings with the audience. Also, I would like to express my appreciation for those of you who attend at 10 o'clock in the morning. And I believe we have all other attendees all over the world joining us. That's the advantage of having this online series. To use time wisely, I need to acknowledge the contributors. It's a big group. We have local academicians, engineers, master, PhD students. So without their involvement, I don't think I'll be able to make this presentation. What I'm going to do today is I would like to give you a chance to have a feeling about what has happened after the event. So I'm going to show a lot of pictures, time is limited and I am very ambitious. I would like to talk about buildings, slopes, excavations, key walls, retaining structures, hydraulic structures, liquefaction, side effects, and so on. Bruce, don't panic. I know I'm not going to spend 2 hours, but probably 1 hour would be enough to go over all those issues. So rather than talking too much, what I'm going to do next is I'm going to show you some slides, and most of the time I'll be just quiet because some of the pictures are self-explanatory, so I don't need to really go into the details of it. Now, what I'm going to do is I am going to go around this coastal region, which is about 20 to 30 kilometers from the source of energy release. I will start with Gümüldür, Özdere. That is the region pretty much like populated with like 4 or 5-story residential buildings. And let's take a look at what has happened there. Some damage to infill walls, not very much significant damage that we need to really talk about. Let's move to Kuşadası and Davutlar region. Oh, a little village building, masonry structure. I don't think those cracks are because of the earthquake, and the building survived after the earthquake. That's why I would like to share this picture, not to emphasize about any damage, but to emphasize when we are in the vicinity of an event, pretty much this non-engineered masonry village type structures survived with very minor damages. Let's move on. Kuşadası, more modern type engineered structures, absolutely positively not much to talk about. They survived. And then now I come to 70 kilometers away from the source in Izmir, Bayraklı region. All of a sudden, the picture will change. I'm going to talk about casualties, heavily damaged buildings, collapsed buildings, and I believe that is the story of this event. And let's take a look at the pictures. This is the foundation. Alluvial deposits. I will talk more about it. We don't have raft foundations here. We'll talk about strip foundations, shallow. You'll see a lot of hinges, shear failures, infill wall damages. Not surprising, we'll see those, but psychologically damaging, because if you live in those buildings and if the infill walls are damaged, then you cannot really explain that to the residents of those structures. Again, you see the hinges at the basements. The picture will get more dramatic. I am so sorry to show this picture. Full collapse of the one side of the basement. A lot of heavily damaged structures. I'll give some statistics. I don't want to give the wrong picture. The building stock in Izmir, what I'm talking about downtown Izmir, is about 670,000. Now I'll just only talk about 110 or 17 heavily damaged buildings. But bottom line, why 70 kilometers away? You see like the fully collapsed basement floor. Debris, they have to demolish them after the event. Poor tie beams, designs, detailing. Whoa, this is not the heavily damaged structure. Some partial collapse. Again, you see the damage on shear walls. Partial collapse. You can see the angle. I'm going to move away a little bit. In that same neighborhood, I'm going to show you some other kind of structures. These are like non-engineered, 1 to 2 story. God knows what they are. Like, I don't think the material is nothing to do with engineering, engineered theories that we have learned, but they survived. This is right next to those 5, 7, 10-story buildings that were heavily damaged. Nothing. In the same neighborhood, there are some structures that were not damaged at all. Again, I'm talking about Bayraklı region. Again, damages on shear walls, columns. You see shear failures. I would like to show some other pictures. Again, this time a little bit in the north west region. Slight settlement and tilting of the structures, but not full collapse. Here's another picture. Not much damage. Let me quickly summarize. By the way, my expertise is geotechnical and earthquake engineering. So the credit goes to my colleagues, Yakut et al., who basically were kind enough to share this summary and conclusion so I can convey it to you. Basically, heavy damage is due to inadequately designed structures, mostly 7 to 10-story reinforced concrete buildings in Bayraklı. 670,000 buildings, 13 full collapse, 110 heavy damage. Infill wall damage caused significant property loss. And it has also a lot of psychological issues because people refuse to get into those buildings, which is understandable. Some of the damage could not be appreciated through street surveys. You have to get into the building to understand the extent of the damage. Infill walls, they really help to improve the performance of structures. So especially at this low level of seismic shaking. Inadequate stiffness and strength of slabs, poor tie beam detailing, those were the major reasons why basically that structural deformations or poor performance were observed. Regular structural systems, continuous frame systems, they lack in those heavily damaged buildings. Excessive corrosion was another factor that we observed. Overhang column connections, ground floor column damages were very much frequent. Reoccupation of buildings was impossible because of those problems at some of the structures. The reason why we observe that damage is because of inadequacies and deficiencies in structural detail. Because the ground motion levels observed were below, as I will discuss in a little bit, below design levels. So I don't think intensity of shaking was the reason why we observed that damage. So let's quickly move on. In a couple of minutes, what happened to slopes? Pretty much no slope failures. Some deep excavations, a couple of millimeter increased deformations after the event, but pretty much no failures on slopes. A few rock falls by the highways, no slope failures. Again, let's look at this retaining structures. Wow, look at them. These are stone walls. And I'm really like, we're now talking about 0.15 Gs of accelerations and no damage. Look at this. They survived. Examples. Other examples. This is same place where we see structures, but luckily no retaining wall failures. Some spillway channel walls, no deformations. Let's take a look at the hydraulic structures. We have a few dams. They all perform perfectly elastically, except that one of them where we have some fissures observed after the event at the interface of the clay core and the rockfill where we have the filter zone. So pretty much no damage at all. Let's take a look at the liquefaction manifestations. Again, this is the area, USGS liquefaction hazard map released after the event. So there are some areas where potential liquefiable sites exist. And I will get those sites, no surface manifestation. So that is valuable. We took some, except at Gülbahçe region. We observed some sand boils. This is the only region where we observed sand boils. We tested those sand boils. They fall in the region where we expect liquefiable soils. Here are some pictures of it. Interesting, basically like in Karşıyaka region, also Mavişehir region, stone columns are widely used to improve ground. And after this event, some of those stone columns, they work as a drain and release some water. That is what was basically shown in the slide, even though we took the picture a little bit 2 days later, so you don't appreciate the water released or drained out. Liquefaction triggering relationships by Chetin et al. Non-liquefied regions, they fall in the region where we expect no liquefaction, so that's good news. The liquefaction case histories will come from Samos Island, Vathi, where we are working on with our Greek colleagues, and there is abundant of liquefaction cases from there. Now the mystery, why we have those damages concentrated in Bayraklı region. Do side effects have a contribution on the observed damage? Let's take a look at it. This is the event. This is the region where we observed structural damages. It's approximately 70 kilometers away. Heavily damaged buildings concentrated in that region. This is one of them, fully pancaked, where basically like pretty much a week efforts were concentrated to save lives. This is Bayraklı region. Gray zones are alluvial deposits. We have really deep alluvial deposits here in Bayraklı region. And I'm talking about 1.5 kilometer deep alluvial deposits. This is the basin surrounded by Nif mountain or hill and Yamanlar. You see how confined the basin is. Again, a typical cross-section there. Some borlogs from the area. We have typically like silty, sandy, clayey materials with some gravels interbedded. Let's take a look at the strand ground motion records. These are all the records. So luckily we have a good network. These are the rock sites. Again, the damage pretty much was concentrated in this zone. So in the vicinity, we have good network on rock sites, soil sites. Wow, this is a perfect opportunity to appreciate side effects. These are the rock records, soil ones, median, median plus one, standard deviation. Just by looking at it, rock accelerations, 0.5, 0.6 PGAs, soils 0.8,
Okay.
maximum is 0.15. Wow, those are not high levels, but look at the spectral accelerations at 1 second. Wow, that is somewhat unexpected. And let's take a look at this story then. Then the question, and here are the basically the rock motions compared with ground motion prediction equations. Please don't ask me which one. It doesn't matter which one you plot. Basically, in this mid to long period range, we have high energy. At rock sites, high energy. That is something we don't expect. Let's find out the mystery. How that, is it because of the source? Now I'm going to go look at what is happening at the source. At the source, Samos Island. Again, that mid to long period energy is there. And when it is traveling to Bayraklı, on the way, that mid to long period energy is preserved at rock sites. That is interesting. That is something we don't usually observe. Let me take the picture. Okay, so starting with, we have high mid to long period energy at the source. When it's traveling to our site, that is preserved, and our deep alluvial soils basically amplified that already rich mid to long period excitation. Here are rock sites again. They're present. Look at it. compared to ground motion prediction equations, that is a little bit unexpected, this region. And by the way, this shaded region is the nature period of the 7 to 10 story buildings that were heavily damaged. Okay, let's proceed. Samos. On the way, that long period is still there. And let's look at the soil sites. Soil sites, ground motion prediction equations, they're doing okay. Rock sites, no, not really. We did some deconvolution studies to understand what is happening at the basin. Deconvolution of rock sites, deconvolution of soil sites. By the way, these are unusually deep deconvolution assessments. So luckily we have the data. Wow. Soil deconvolution, rock deconvolution. The match is nice. So we increase our confidence. We have a good basin motion. Mr. Mason, I am completing. Don't worry, in a couple of minutes, I will conclude. We perform those, use those within motions, perform site response analysis. Yes, we could really match what is happening or a good match was obtained with the available records. But that is one-dimensional assessment. We're talking about a basin. Right now, we're working on 2D and 3D assessments to understand what is happening in Bayraklı Basin. Just a little premature presentation of our findings. Look, within motion, how it is amplified when it's coming to the surface, and look at the formation of coda. The duration is totally stretched. So that also contributed to the observed damage. One last slide. These are the amplifications. Ladies and gentlemen, one conclusion. These are not in compliance with NIHRB or Eurocode or Turkish code-based amplification values. So definitely Bayraklı Basin is a special basin, or Izmir itself, Izmir Bay, is a special place that deserves special attention. These are the comparisons. As you see that the amplifications at certain periods are beyond what was predicted by the code. Again, back to my original statement, these are design basis spectra for soil or rock sites. So as you see that this event is not even close to the design basis demand provided by this 475-year return period. This event was more of a 72-year return period event. However, at the period range of 0.5 to 1.5 seconds, significant amplifications due to side effects really amplified the response or seismic demand from the overlying structures, which was also accompanied by poor structural design details. I would like to appreciate and acknowledge my contributors one last time, and every event has a human aspect. We're talking about this events from scientific point of view, but there is also a humanistic point of view. This cutie was stuck in the rubbles that you saw in the pictures that I showed you for 65 hours by herself. And when she was saved, she was holding the hand of her hero. And this is the picture taken the next day in the hospital. Luckily, she survived, but not very many were as lucky as she was. Thank you so much. I believe this cutie is the face of this event.
Okay, thank you. Thank you, Kamal. We're running a little bit long, so what's going to be the penalty will be our question and answer period at the end. I'm afraid we probably will not have much time because we will give required time for the last of our two speakers. I'd like to move on to our next speaker. This would be Musan Alfin Bahar. He is with the Turkish National Insurance Pool. He will present on damage from an earthquake insurance claims perspective. Please proceed.
Hello, thank you for your invitation and for this chance to talk about what we do in Turkey as TCIP. First of all, I have to talk about what TCIP is doing before we proceed with Izmir earthquake event. I won't talk about the seismicity in Turkey. It's quite active in Turkey. Most of the people talk about it. We were founded after the August 17th and November 13th in 1999 earthquakes in Marmara region. And we are in 2000, year 2000, and we are still going on. What's the purpose of TCIP? It's especially to cover earthquake insurance, to provide earthquake insurance at reasonable prices for people with average income. That's what our first of all objective, and the details are going on this. The protection and claim payment capacity of this Turkey of TCIP is about 30 billion Turkish liras nowadays. It's about 5 billion US dollars in US dollars. We have a unique organizational structure. We are a good example of public and private partnership because although TCIP is a governmental institution, it is managed by a private reinsurance company nowadays, and with a special agreement between the Minister of Treasury and Finance. The Turk Restaurants, which is a very young reinsurance company, this is the second year, is now managing the TCIP of Turkey. We, as TCIP, provide the earthquake insurance for civil buildings and for buildings, and all the insurance companies and agencies are acting as an intermediate to us. They transfer their policies directly to TCIP, and we handle all the claim operations by this way. It's not an usual organizational structure. It's really interesting, and it's getting hits by other countries too. What's our product? We just sell earthquake insurance policies with a single line. It's just for earthquake, it's just for residential buildings, and TCIP is the only provider, and everything is simple. We have also a simple tariff for premium calculations too. What we are now, we said we provide earthquake insurance with affordable prices. Turkish liras 162 is about 20 US dollars nowadays, maybe less than 20 US dollars. It's for a year of premium. When you compare with the ones US, I think you can understand how affordable it is. When in 20 years, 21 years, the insurance penetrations improved from 4 to 56 nowadays. And we have our good reserves, strong reserves, and we have a good public awareness, product and brand recognition through people. We have a low-cost operation, and we are a market developer, especially for homeowners policies. They are following our policies from a little steps behind. Here is the steep where we are going from year 2000 till now. When we come to the regional penetration ratios, Marmara region is at the top nowadays with almost 70% of penetration, and Aegean coast and Aegean region is following with 59%, and the rest can be seen on the slide. Yeah, when we come to the earthquake propensities, especially Izmir here, the penetration ratio has raised from 57 to 83 in about 1 year after the earthquake, and the rest can be seen on the slide. Especially Istanbul is about 70%. And all the Marmara region cities are over 70% almost, and but Istanbul is a very heavy for penetration. So Marmara is almost 70, following Istanbul. When we come to Nat Cat operations, it's a really complex thing after such an earthquake event. You have to manage the loss assessment process. You have to manage the loss adjuster. You have to do everything about the reinsurance. And you have to be in coordination with the other institutions of the governments, and you have to do everything in a very steep, very managed, well-managed way. So we have started a cat management program in 1920s, following the one earthquake in eastern Turkey. So we raised a disaster management system. We changed our system, software system, in 2019 with a project. We have also created a decision support system of which is based on GIS systems. That we call it the disaster risk management system. Although it's for decision support, although it's for decision support, it's one of our very important tools for managing the operational system at the site. We also manage the claims with a mobile system that's connected to our claims management system. It is for rapid claim assessment with a simple methodology, and we also use it for cost control, and we have about 22,000 receipts of for claims assessment to monitorize to financially monitorize the earthquake, and these are all in live since 2016, and we are still trying to improve them for very hard times. This is all designed for Istanbul earthquake. We are trying to improve it all the time. These are the projects also in live. So the disaster call center project, it's a part of it. Nowadays, in normal days, we have about 20 MTs for taking our calls. But in case of a big event, we can improve it to increase the number of MTs, agents, agents up to 500 in about a few weeks. It's a part of CAT management structure in Turkey. We also have contingency resources and need adjusters for contingency adjusters for big events. That's why we have a contingency deal with the Ministry of Environment and Urbanization in case of a big earthquake. We will also use their technical staff in order to handle the claims, and we also take it very important to use a common methodology for building the loss assessment with them, and we are still working on it, and we have almost finalized it, and it will also upgrade our speed for in the next few years. When we talk.
Musan, we're running way over. I regret, but could you please?
Okay. I will just give you a slide, a few minutes, and I will tell you about Izmir event. But for this, I need a few minutes. In Izmir, we had about 30,000 claim files. This came in about a few months, and we handled, and the city of Izmir, central of Izmir, was about 25,000 files. We handled almost all of them. We finalized almost all of them, and paid about 380 billion Turkish liras since yet. It's the closed number of files is about 89%, and the rest is due to the late coming files. That's why this is the rate. We haven't finalized it. but in the last 2 years, with including the Elazığ earthquake in 24th of January in 2020, it's also a big claim. We are still on it, but we have also almost finalized it. They all matched together, and that's why, although we have finalized most of the files with the use of these technologies behind us, we could improve our speed up to this point at the moment. And also, what I need to say, we are all as TCIB, we think it is important to increase insurance awareness between the community of Turkey, and that's why we are doing PR activities like building design contest. It is one of the unique ones on all over the world. We have also daily and usually PR activities going on. Thank you for your attention.
Okay, Busan, thank you so much. Okay, I apologize that our program's running a little long. We have one speaker, and they will run over to give them their allotted time. So if the audience can stay on after a little bit longer than our 90 minutes, we would appreciate that. And I apologize. Part of the problem was my getting so enthusiastic that many of the speakers ran over. I'd like to introduce our next speaker, Dr. Neslihan Okaklu. She is a professor in the Geophysical Engineering Department of Istanbul Technical University. She will discuss subsea exploration aspects. Neslihan, please proceed.
Thank you very much. Can you see my presentation?
Could you put it on presentation mode so the toolbars go away? Thank you.
Thank you very much. First of all, I would like to thank Dr. Volkan Sevilgen and EERI for inviting me to this webinar. Today, I will talk about the previous marine studies and ongoing projects around the Quake area. As we know that the Samos Quake was very strong quake and caused very strong destruction and severe shaking in the area. You can see the collapsed buildings both in İzmir Bayraklı and also in Samos Island, and also tsunamis effect. So we know that the earthquake occurred with a magnitude of 7 along the approximately 35 kilometer long north dipping normal faulting with a 15 kilometer width. And many people died, more than 100 people in Turkish side, and many people injured, thousands of people injured by this quake. So you can see the east-west oriented normal faulting. If we look at the recent quake fault mechanism solutions and also other instrumental quake solutions, we can see the both active expansion and strikes with deformation in the study area. This is the main shock, and if you look at the aftershock, so there are some clusters here, one of them in the eastern side, and the other one is very particular in the western side with the strikes with deformation. So in historical period, we know that the area is very active seismically, but this earthquake was very particular because it was the first earthquake with the magnitude of 7 in the last 19th centuries. So this was very important. If you look at the rupture propagation, the rupture started from eastern to western, and it's propagated toward western, and there is also another segment here. And also Coulomb stress model indicates that while the stress decreasing in the northern and southern, the stress increasing at the eastern and western side. Let's see, next slide. We know that the general tectonic framework of Turkey, there's a westward motion of the Western Anatolia and counterclockwise rotation, and very fast movement toward the Hellenic Trench. So this recent deformation is controlled by the normal faulting in both countries, in Anatolia and Greece, while the strikes deformation in the northern and middle Aegean Sea. So it is very strange because the recent study is saying that the stress transfer from the extensional to the strikes deformation toward the Aegean Sea. So because we know that the counterclockwise rotation and recent northeast and southwest extension in this area. The seismic is also very compatible with the fault plane solutions. If you look at the study area, we can see the pre-Miocene and post-Miocene tectonic features of the Izmir region. I want to show the whole area because all these structural trends extending from the Izmir Gulf toward the southern area, toward the Quake area. Kaya et al. Indicated the area as a Neogen depression area from north-south to northeast-southwest trending blocks as a pre-Miocene structure. But Axe et al. For the younger structure, they map several normal faults in east-west and north-south, northeast-southwest direction. As we know that from the on-land studies, there are many strike slip faults here, extending in northeast-southwest direction. This is the Zeytin-Dağ-Bergama fault zone. And another one is Tuzla fault zone. It is very important. It's a right lateral strike slip fault zone because in the 2005, there are two earthquakes there with a strike slip focal mechanism. And also Karaburun fault with a reverse character, it's an important. So as you see that their geometries are very different than the boundary faults of the graben. These are extending in east-west direction with a normal character, but these are extending in northeast-southwest direction with a highly strike slip character. So as we know that there is a normal faulting by the last quake. If you look at the geology of Izmir region, we know that the rocks gets older from eastern to western side, but very soft rocks around the Izmir city Bayraklı, as Professor Çetin said, very thick soft sediments causes the amplification and huge collapse. And also we can see that the north-south in northeast-southwest trending structures. If you look at the Samos Island, it is very comparable with the Izmir region, again north-south trending older NAP units developed under compressional tectonics, so as you see north-south thrust, and younger east-west oriented normal fault exists on the Samos Island. So the first multi-channel seismic study in marine area was performed in 2000 by the Turkish scientific team, TÜBİTAK. So this was my PhD study. Actually, the approximately 900 kilometer multi-channel 2D seismic channel were collected, and the data were processed conventionally in the Department of Geophysical Engineering of Istanbul Technical University, and time-migrated seismic sections were interpreted. Additionally, we prepared a detailed topography map of the Izmir region with the precision of 75 meters. So again, we can see these faults as a Karaburun faults, Urla faults, and Tuzla faults, and other lineaments extending from north-south to northeast-southwest. So dominantly exist in the area, and some east-west oriented Izmir fault, Bornova fault, and the normal faults of Küçük Menderes Graben. And also we can follow these faults and lineaments on land photos. So as you see, on the Karaburun Peninsula and on the Alaçatı and Teke land area. So then we interpreted the seismic sections stratigraphically. We correlated the seismic units with the Foça Bir well, which was drilled the Turkish Petroleum Company in 1919s. So there are two main unconformities here. The one of them is the upper Miocene, lower Pliocene unconformity. It is a widely mapped in the Western Anatolia, and the other one is another unconformity within the Plio-Quaternary rock. So we can follow this unconformity both within the Gulf of Izmir and also offshore Seferihisar. So you can see this erosional surface. Mapping this acoustic basement, let's say the upper Miocene basement, indicates that there is a sudden deepening basement in the steady area close to the Quake region, and also some basin and reef structures. So this is very strange because the Gulf of Izmir is not a whole graben extending in northeast southeast direction. We can see that there is an inner and outer gulf separating by a north-south oriented reefs. So this, I want to say that there are reefs and basin structures within the Izmir region. If we can say that the Karaburun reach and another reach within the Izmir basin and Seferihisar reach here. So these reaches are controlled by the strike slip faults. Now let's see the next slide. Now let's focus on the study area, offshore Kuşadası, Seferihisar, and Alaçatı. If you look at the seismic sections, so we interpreted several faults with a strike slip character. These are the black one, and some faults with a normal character. So you can see the 20-meter vertical displacement offshore Kuşadası graben. So this is another seismic line, also again offshore Kuşadası graben, a highly faulted area. We can say that the many strike slip faults and very little normal faults. So the top set and foreset transition with a 128 meters, it's lower than the last glacial maximum level. It's around 110 meters. So actually this indicates there is a subsidence in the area. But we know that the extension is in very little in the Western Anatolia in this study area, a few millimeters per year. There is only north-south extension exists. Now let's see another seismic section, again offshore Küçük Menderes graben and offshore Kuşadası. You can see the thick sediments of the Küçük Menderes River and some non-active normal faults and active strike slip faults. You can see the effects of the strike slip faults. They are very steep faults and they have a flower character, some of them. Now let's see what's happening offshore Doğan Bay here. So at the western side of Doğan Bay, again, we can see the strike slip faults. And yes, this is very important fault zone. Tuzla fault zone, here, we are here. And this is the Tuzla fault zone. It's a huge strike slip fault zone with a positive flower structure, and also it has a reverse component. So in that area where the faults rotated to the north-south direction, they have a reverse component. We can see that. Another one is offshore Teke. Again, you can see the very young strike slip faults and non-active normal faults in that area. So deepest vertical displacement in that area, offshore Teke, with a 74 meter, there's a vertical displacement. So we know that there's a very dramatic the basin deepens in that area. So we know that there's an EERI basin here. So EERI basin, one of the deepest basins in the Aegean Sea, it is approximately 1,100 meter depth. Now let's see another strike slip deformation offshore Alaçatı. So you can see these are the strike slip also. If you look at the whole 2D seismic sections together, we can see that this fault is extending from northeast to southwest direction, which they are very compatible with the on-land active faults. So if we correlate with the offshore and on-land active faults, we can see that the area is widely covered by the strike slip faults, and strike slip faults intersect and displace the normal faults. So as we know that there is no continuous normal fault of the Küçük Menderes graben within the marine area. You can see, instead we see the strike slip faults, and we can see very short distances normal fault, which was cut by the strike slip faults. So we can define this area by this 4 strike slip fault zone. If you look at the whole picture, we can say that the area under the strike slip deformation, it is very different than the Western Anatolian grabens, and we can explain the area with a pure shear model, whereas the north-south extension causes the east-west shortening and northeast-southwest oriented right lateral and northwest-southeast oriented lateral strike slip faulting. If we look at the GPS vectors and the seismicity, in 2005, we proposed a cartoon model because we thought that the Tuzla Fault has a very regional importance in that area. And the Tuzla Fault zone, the microseismicity indicates that the Tuzla Fault zone probably extends more than that we know, and separates the area into two different areas, the northern Aegean and middle Aegean Sea. There is under the shortening, it has compression because of the resistance of the Greece in the western of the Greece land area, and the southern more extensional area in the northeast southwest direction. But what we don't know where is the extension of the Tuzla Fault zone in the Quake area. So if you look at one of the recent studies by Casaras et al., and the stress shape from the inversion of earthquake focal mechanism. So as you see, the compression and extensional vectors are very support our proposed model here. So you can see a transition zone here. Later, this transition zone is interpreted as a İzmir-Balıkesir transfer zone by the 9 Eylül University researchers. But they say that this was a not right lateral transition zone. But we know that the recent seismicity, recent activity, this fault is a right lateral strike slip fault zone. Again, we go back the study area. What we know the active faults here with the strike slip and partially normal character, and the Quake area is here. And also there are some normal faults we know by the Lecas et al. This is the Samos fault, and there are some other normal faults with different geometries, boundary Ikaria basin, and also there are some other strike slip faults separating the Samos and Ikaria basin. So at that point, the researchers think that the faults of the Küçük Menderes Graben continues is like that to the western area, but there is no such thing in that area because there are different fault segments in this area with a different geometry and with a different fault character. From the recent studies, so one of my colleagues from the Greece, Nomikio et al., published a marine research after the Samos quake. So he published the multi-rim bathymetry of the Quake area, so as you know, and they mapped the several normal faults. Actually, they proposed a normal fault with a north deep with the 45 degrees. And you can see this normal fault and Quake point, and there are also some currents and landslides and escarpments and some other things. Unfortunately, we have no adjoint project with the Greece because of some political problems. But fortunately, after the outputs of this project, now currently the Turkish team and the Greece team studying separately, but we hope that the outputs will be complement to each other to understand the active tectonics of this area. I want to show you also, this is very important. This is very old study, but the seismic data is very important. So the scientists think that the area is under the transtensional deformation and there are transfer faults. So we should think that, so when you go to the southern area of the Samos and Ikaria basin, you can see that silent zone on the seismic section. But, when you go to the northern area of the western and northern of the Ikaria basin, so you can see the tilted blocks associated with the reverse faults, and you can see the strike slip faults with a compressional component. So the area actually, it's a real tectonic puzzle. So at that point, some questions arises. The first one is, at what distances do these strike slip fault zones continue in the Quake area? This is the first question. The second one, what are the geometries of the strike slip faults and normal faults in the Quake area? And the last one, how can this fault pattern can be explained by the current tectonic region? This is the last slide. This is the ongoing TÜBİTAK research project. So the coordinator is Dr. Gülsen Uçarkız from the Geological Department of Istanbul Technical University. I am the one of the researchers of this project. Our aim is within this project to investigate the seismicity and active tectonics offshore Kuşadası with high resolution seafloor measurements. First of all, we should know the morphological features in detail with the multi-beam bathymetric data, and then we aim to compare these morphological features with the previous seismic studies, and then we want to combine these outputs with the marine studies of the GRIS team. Thank you very much, and thank you for your attention.
Thank you for your presentation. It was very interesting to me to see how subsea exploration is done, as you explained. We're running over on time, so what I would like to do is thank all of our presenters today for taking the time to give us presentations. And I appreciate the efforts they put in. What I'd like to do now is turn control over to Volkan to make various comments. Please, Volkan, could you proceed?
Thank you, Bruce. Thank you for all the presenters. This has been a very loaded series of presentations, and I'm sure many of you will have a lot of questions. And what I would suggest that you can send emails to each presenter with various questions, and bear in mind that everybody is under time pressure, so they have no obligation to answer your questions in timely manner. We will continue having these seminar series, and we would like all of you to join this seminar. These are free. You don't have to be part of the EERI membership, or you don't have to be part of our chapter. So you can advertise these webinars to all of your colleagues and invite them to these webinars. Of course, if you would like to become our member, we would be delighted. But you don't have to for these webinars. So I think I would just close the meetings because we are over time, and hope to see you again. Thank you.